This is section 1.9b, inverse functions. First, let's talk a little bit about functions in general. And you recall we did this earlier on in the chapter, but it never hurts to repeat things because every time you see something again, you learn it just a little bit better. Okay, so remember that a function is a relation that assigns each element in one set of numbers, the domain, to exactly one element in another set of numbers, the range. And if you want to review your notes on this, you can go to section 1.4 and section 1.5a. So anyway, this is the definition of a function. And we saw the vertical line test in section 1.5a, so let's just quickly review that now. The vertical line test both illustrates this definition of functions and also tells us whether a particular graph is a function or not. So let's look over the vertical line test again. This is a function. This happens to be a cubic function, and it doesn't matter what the specific numbers are. This is a typical cubic function. And we can see that if we apply the vertical line test, the vertical line intersects the graph in only one point, and therefore it passes the vertical line test, because remember that the vertical line test says that if the vertical line crosses the graph of a function or a relation in any more than one point, then that graph is not a function. Okay, so here is an ellipse. This is a conic section like what we learned in chapter 10. And an ellipse is not a function. Okay, it's not a function. It is a relation. It relates x and y, specifically x squared and y squared, relates those, but it's not a function because it doesn't pass the vertical line test. And the vertical line test is really just an expression. It's a visual expression of the definition of a function. Because, all right, let's look at what the vertical line intersections say. What they say is that, okay, look at where the mouse arrow is right now. I've got it hovering there over the ellipse. Okay, what these red points say is that for this particular x-coordinate, and it looks like this x-coordinate is negative 1.5. Okay, and you can see that right here on the grid. Okay, so it looks like this x-coordinate through which the vertical line passes is negative 1.5. Okay, well that x-coordinate would be a member of the domain. But that member of the domain happens to be matched with, or as they often say in relation and set talk, it happens to be mapped to two different y coordinates. Two different y coordinates. Okay, notice that these two red points share an x coordinate and they differ in the y coordinates, but that violates the definition of a function in which the element, or each element in a domain, is matched to or corresponds to exactly one element in another set of numbers, the range. And in this case, the member of one set, negative 1.5, the x-coordinate, our would-be domain, that negative 1.5 member of this domain happens to be matched to two different members of the range, and therefore this is not a function because it violates the definition. Okay, so that's just a quick review of functions and the vertical line test. Why are we doing this now? Because it has to do with inverses, and we're going to see that now on the next screen. So this brings us to a subset of functions called one-to-one functions. All right, so all one-to-one functions are functions. Duh, right? All one-to-one functions are functions, but not all functions are one-to-one functions. Okay, I'll say that one more time. All one-to-one functions are functions, but not all functions are one-to-one. Okay, so one-to-one functions are simply a subset of functions. A function f of x with domain D and range R is one-to-one if for every value of f of x in range R, there is only one value of x in domain D that corresponds to it. In a non-one-to-one function, several different elements in a single domain can be matched with the same element of the range. For example, in the sine function, you've seen the shape of a sine wave. It goes up and down, up and down, up and down. And so for an infinite number of x values in the domain of the sine function, you can have a repeated value in the range. You can have a repeated value of 1 or 2 in the range, and that can be matched with many different elements in the domain. However, in a one-to-one function, you only have one element of the domain for each element of the range, and only one element of the range for each element of the domain. A function f of x has an inverse function only if f of x is 1-to-1. Alright, so remember when we were doing matrices, not every matrix was invertible. Well, the same is true of functions. Not every function is invertible. The only functions that are invertible are one-to-one functions. A function f of x is 1-to-1 only if the graph of f of x passes the horizontal line test. That is, only if no horizontal line intersects the graph of f of x in more than one point. Alright, so we've seen the vertical line test to see whether something's a function or not. Well, once you know that something's a function, you can further apply the horizontal line test to see if that particular function is a one-to-one function. For example, the function f of x equals x squared minus 4x plus 7 is not 1-to-1 because the line y equals 7 intersects the graph at both 0, 7 and 4, 7. So if we put the line y equals 7, just a random horizontal line, that horizontal line passes through the graph of the function in two different points, 0, 7 and 4, 7. Now we can see that the element of the domain 0 is matched with the element of the range 7, and the element of the domain 4 is matched with the element of the range 7. But that's not one-to-one because in a one-to-one function, each element of the domain is matched with exactly one element of the range and vice versa. And that is not true in this case. So this parabolic function fails the horizontal line test, and therefore it's not one-to-one. Example, apply the horizontal line test to the graphs below to determine if the functions are one-to-one. Y equals x cubed. This is a rough graph of y equals x cubed. So try to do this on your own. Pause the video and then resume when you have an answer, when you've determined whether it's one-to-one or not. Okay, so you're probably able to see that it is one-to-one because it passes the horizontal line test. And obviously it also passes the vertical line test, otherwise it wouldn't be a function. But it passes the horizontal line test, and this is a one-to-one function. How about y equals x cubed plus 3x squared minus x minus 1? Is that a one-to-one function? Pause the video, come up with an answer, and then resume when you have an answer. No, it is not a one-to-one function because not every horizontal line that you can draw through this graph will cross in only one point. Obviously, there are certain horizontal lines that would. You can see that if you drew a horizontal line down here, it would cross in only one point. If you drew a horizontal line up here, it would cross in only one point. But since there's a region where if you draw a horizontal line, it can cross in more than one point, then it's not a one-to-one function. To find the inverse of a function algebraically, interchange x and y and solve for y. Alright, so now we're going to go through the technique of actually calculating the inverse of a function. For example, find the inverse function algebraically for the function f of x equals 3x plus 2. Well, here's how you do it. First, you just write out the function, but you also write it in terms of y, simply because y is easier to work with. It's one letter instead of two letters, and there's no parentheses. So remember that y is often a synonym for f of x, but in this case, when we're doing our calculation, we're just going to write it as y for the sake of convenience. X equals 3y plus 2. This is the key step in finding inverse functions. You're just switching x and y. because really that's what an inverse function does. We saw that in the last section. It switches the x's and y's. It also switches the domains and ranges. Okay, so that's reflected algebraically in this step. You're switching x and y. Then what you do is you solve for y. Alright, so if you want to get y by itself, you subtract 2 from each side, and then you have x minus 2 equals 3y, and then you divide by 3 to get rid of the 3, and you end up with y equals x minus 2 over 3. Okay, now the final step is simply to use function notation, because that y that we just calculated is the same as f inverse x because we swapped the x's and the y's. And so f inverse x equals x minus 2 over 3. This is the process for calculating the inverse function. Here's another example. Does the function f of x equals cube root x plus 1 have an inverse? If so, what is it? Alright, so here's what you're going to do. You're going to graph the function, and that will allow you to apply the horizontal line test. That's going to tell you whether it has an inverse or not. And then, based on that answer, you can try to find what the inverse is. So pause the video, try to do this all on your own, and then resume when you have an answer or if you get stuck. Alright, so the first step is determining whether the function has an inverse or not. And we do that graphically. So, this is what you should have gotten on your graphing calculator. For those of you who, by the way, are having a little trouble with your graphing calculator or aren't sure how to do cube roots, often what you can do is just enter the quantity as parentheses x plus 1, for example, in this case. Enter the quantity, so you'd put parentheses x plus 1, and then you would raise it to the 1/3 power. Okay, so raising that quantity to the 1/3 power is the same thing as taking the cube root of it. So anyway, this is what you should have had on your graphing calculator, and we see this kind of S-shaped curve. This is the graph of cube root x plus 1. Now if you do the horizontal line test, you can do the horizontal line test in any point in this graph, and you'll find that it passes the horizontal line test. So we just do a horizontal line in any random place, and when we do that, we see that it passes the test, and therefore it's a one-to-one function. Alright, so now that you know that it's a one-to-one function and that it has an inverse, you need to calculate the inverse. So we're going to go through the steps of calculating the inverse. Alright, so f of x equals y equals cube root x plus 1. This is our first step. We're just writing out the function, but we're also putting y because, for the sake of convenience, it's easier to work with. Now, this is the key step. We swap the x's and the y's. Again, why do we do that? Because with an inverse function, that's exactly what you're doing. You're swapping x's and y's. You're swapping domains and ranges. Okay, so x equals cube root y plus 1. And then what we do is we solve for y. So we have x cubed equals y plus 1. X cubed minus 1 equals y equals f inverse x. F inverse x. So we have now found f inverse x. X cubed minus 1 is the function. Now let's look at the graph of f inverse x. Now I know that this problem didn't ask you to graph the inverse, so that's not required or anything. But the reason I want to show it to you now is just so we can better learn how inverses behave and what their graphs look like. Alright, so this is the graph of f inverse x. Okay, so I have on this set of axes here, I have two graphs. I've got the graph of f of x equals cube root x plus 1. And I also have the graph of that function's inverse, f inverse x equals x cubed minus 1. Now, notice the symmetry. Notice the symmetry. These graphs, as we described in the last section, are symmetric about the diagonal line y equals x. So I've drawn that diagonal line y equals x with a dotted line there, and you can see how if you were to pretend this graph were on a piece of graph paper and you folded it over using that dotted line as a crease, well, you would have a mirror image. You would have the exact same thing on the other side because the diagonal line y equals x is acting like a mirror here. And so inverse functions are symmetric about the line y equals x. So functions that are inverses of each other show this kind of symmetry. But anyway, we've seen that before. This is just to illustrate it. Next example, does the function f of x equals x squared have an inverse? If so, what is it? Alright, so pause the video, do this on your own, and then resume when you've found the answer. Alright, first step, you need to determine whether it has an inverse or not. Alright, so you need to graph it. And you should have gotten this on your graphing calculator. And then when you apply the horizontal line test, we can see that it does not pass the horizontal line test. And therefore, no. This function does not have an inverse. Next example, does the function f of x equal x squared with its domain restricted to 0, infinity have an inverse? Now notice that this is similar to the example on the last screen in which we were graphing f of x equals x squared. But here's the important difference, and this is where you have to pay attention because there are times where the domain is specified and restricted. Now normally the domain for the x squared function, the parent quadratic function, normally its domain is all real numbers, but we can restrict its domain, and so here the domain is restricted to the interval from 0 to positive infinity. Now there's no intrinsic reason for restricting domains. There's no mathematical reason why you have to do it. It's just that you can do it. Alright, it's just that you can do it. And in this case, if we're restricting the domain to the interval 0 to positive infinity, that might change things a little bit. So pause the video, do this on your own, then resume when you have an answer. Okay, this is probably what you came up with. If I restrict the domain from 0 to positive infinity, then the graph of f of x equals x squared looks like this. It looks like half a parabola. Now in this case, when I do the horizontal line test, you can clearly see that this function passes the horizontal line test. Of course, that's a terrible horizontal line I just drew, but you get the point. You know, any horizontal line that you draw through this graph passes the horizontal line test. Therefore, the answer is yes. Yes. The function f of x equals x squared with its domain restricted to the interval 0, positive infinity, does have an inverse. If so, what is it? This is the next step, which you should have done on your own. If you didn't, pause the video, try to do it on your own, then resume. F of x equals y equals x squared. Next, what we do is we swap. So x equals y squared. Then we solve for y, root x equals y, and that equals f inverse x. F inverse x. All right, now let's look at the graph of these on the same set of axes, and we have this. We have f of x equals x squared, and we have f inverse x equals root x, and we can clearly see the symmetry. These two functions, the graphs of these two functions, are symmetric about the line y equals x. The last example, does the function f of x equals 5 minus 3x over 2 have an inverse? Does that function have an inverse? If so, what is it? Pause the video, do this on your own, and then resume when you've answered both questions. Alright, so this is the graph of f of x, and we can clearly see that it passes the horizontal line test. Therefore, it is 1-to-1, so yes, it has an inverse. If so, what is it? Now we just go through the steps. F of x equals y equals 5 minus 3x over 2. Swap x's and y's. X equals 5 minus 3y over 2. 2x equals 5 minus 3y. 2x minus 5 equals negative 3y. 2x minus 5 divided by negative 3 equals y equals f inverse x. Alright, so putting those graphs on the same set of axes, this is what it looks like. we have our function f of x equals 5 minus 3x over 2. We have its inverse, f inverse x equals 2x minus 5 over negative 3, which we've calculated. And again, we can clearly see the symmetry. We can clearly see that these two graphs are symmetric about the line y equals x. And you can also see, of course, that our x's and y's are swapped. You know, here at this point, right here where I got the arrow, you can see where that, where that crosses the x-axis. You know, that corresponding point, which looks to be, it's between 1.5 and 1.75. So let's just call it, 1.65. That 1.65 x coordinate is reflected here with a 1.65 y coordinate. And notice that at this point, the x coordinate is 0, just as for the corresponding point of the inverse function, the y coordinate is 0. All right, so the x's and y's are swapped. Here's another point over here that I'm just going over with the mouse arrow. You can find that where I'm circling right now. Okay, that is the ordered pair 2.50. Well, if we look at its counterpart on the inverse function, we have the ordered pair 0, 2.5. Okay, so x's and y's are swapped. Classwork, page 100. Write these numbers down, and we'll see you in class.